This is the Amp Hour Podcast. Released June 30th, 2024. Episode 672. Silicon Revolution with Matt Venn. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Matt Venn of the 0 to ASIC course, Tiny Tape Out, and Yosis HQ.
Welcome back, Matt. How you doing?
Yeah, I'm doing well, thanks, Chris. How's it going with you?
Good. I've been watching with fascination as you continue to just crank stuff out, and your community cranks stuff out, and the Silicon Revolution is here, I think. Is that a fair?
Yeah, just waiting for my silicon 3D printer from Sam's Aloof, and I'll be set.
Yeah. Oh, yeah. Atomic. Atomic something? Just atomic.
Atomic semi. Yeah.
Yeah. Yep. Well, we'll see. Yeah, I've been trying to get Sam back on too. So, in the meantime, I think you're still using traditional, just the good old, the old ways are the best ways, huh?
Yeah, the well established. Send it off to a factory, wait 6 to 9 months, and then hope it works.
That is pretty wild that it's still 6 to 9 months. But I mean, I get it. I mean, I've seen how it works. I know the economics of it all, but like that's a long design cycle.
Yeah, there's a fab like Global Foundries will do a turn in like 3 months.
Right, and if they already have the mask set, like the actual manufacturing could be less, right? If they're moving towards volume, they could get down to like a month, maybe. But
I think it's still longer than that because it's just a very deep pipeline with a lot
300
of
plus steps.
Processes.
Yeah, exactly. Yeah, and just like capacity issues and all that stuff.
Yeah.
I think Samsung, when I was there, they were down to like 35-day turns, but then that was just to just have a wafer, and that's not where you stop, right? I mean, you're getting packaged chips that are tested.
Yeah,
right?
The wafers have to be diced and then picked and then packaged, and then they send them to me, and then we send them on to the contract manufacturer. Then they get warehoused and then sent out to the customers.
Yeah, that's a long cycle for sure. That's very impressive. So you were back on in January of 23. We're going to talk. That was episode 616. Obviously, we'll link that in. Matt has once again, I think I mentioned this in the last episode, Matt has sent gobs of links, which is very, very much appreciated. This guy, if you're worried that Matt Venn is not organized with your chip stuff, you should put your mind at ease because he is very organized.
That's not what other people say.
Okay. All right. Well, no one's going to be happy every time, but yeah. What has been happening? So where were we? I guess paint a picture for us where we were in January 23. That was 18 months ago.
Yeah.
So
we just sent off Tiny Tape Out 2. That was the big news. So Tiny Tape Out 1 was basically a minimum viable product with a MailChimp sign-up page and a Google form, and that was it. But we had maybe 150 people submit designs. It turned out to be a lot of work because it was so kind of hanging together by loose threads. Can
you remind people what Tiny Tape Out is as well? We've definitely mentioned on the show outside of the thing. Yeah,
I think it's fair to say that everybody knows what Tiny Tape Out is by this stage. Don't you think?
You never know, Matt. We have so many new listeners. Just they're just rushing the exit. They're rushing the entrance. Like they just want to get here. Yeah.
Okay, so if you're a big firm, then you design a chip and you tile as many of them as you can across a reticle, which is the mask used to project onto the wafers. And then those are stepped across an entire wafer. And then the wafer's diced and you get however many chips you get off a wafer. So if it's a small chip like an RFID chip, you might get 150,000 chips. And if it's a big chip, you might just get 20 or 30. But to do that, you need to buy those masks. And there's like 50 masks. And the ones that pattern the MOSFETs, have the smallest features. They're the most expensive. And a whole mask set for Sky 130, which is an open source manufacturable PDK that we have access to, is 20 years old. the masks are still $200,000 for a whole set. So you pay up your 200 grand, you get your masks, and then you're paying about $2,000 or $3,000 per wafer with however many chips are on it. But if you're wanting to prototype, you'd like to save money. So instead, you hook up with another 39 people on what's called a multi-project wafer. So in our case, eFabless is the company that runs the Skywater multi-project wafer. They take 40 designs, combine them into the one reticle, step that across the wafer, and then you get maybe 20 or 30 of your chips off each wafer. They run just 5 wafers, so you get about 100 chips in total. But you only have to pay $10,000 for that. So if you want to do that now, you can just go to eFabless, send them your stuff, pay 10 grand, you get 100 QFN packaged chips 6 to 9 months later. But that's still a lot of money. And the Google sponsorship of the Google sponsored free lottery hadn't ended at the time of Tiny Tape Out, but the lottery aspect of it was fairly annoying for me, at least. Other people as well, because you put a lot of effort into the design and then you don't know whether it's going to get made. And I was always working with like 16 people at once, say, everybody would be working. We'd all put it together into one design that we would then send to eFabless. So I was already concentrating multiple projects onto the die at that point. And I just thought, what if we just bought an eFabless chip ignite slot and then like divided it up into 150 or 300 or 400 tiny slots and sold each of them? Then
and so this is now the 10,000. This is the 10,000 wafer, the $10,000 product that now you're subdividing again to 150.
Yeah. So it's like I think technically it's called a multi-project chip, and we're using a multi-project wafer service to manufacture it.
Okay.
So, and the current version of Tiny Tape Out fits up to 512 projects on one die.
Why are there only 150 slots then? Is it because people get multiple projects?
150 slots.
Didn't you say there's 150 slots out of the Tiny Tape Out?
For Tiny Tape Out 1, we got 150 people to submit a design.
Oh, I see. Okay. All right. So that was not a full...
we were playing around with kind of what size makes sense. So now the tile size, that's what we call it, for the little area that you get, is kind of 150 microns by 100 microns, and it's enough for about 1,000 standard cells. So you can squeeze in a very tiny RISC-V processor or a VGA driver or an FIR filter or PWM generator, these kinds of little projects.
Yeah. And then now this is tied to the stuff that Uri was doing on Walkwe that then enabled all this to happen, right?
Yeah. So we wanted a way of not just handling Verilog and HDLs, especially for working with complete beginners or high schoolers, say. So a schematic-based design entry system. So I'd met Uri through Hackaday, and we started. He took my 0 to ASIC course and rinsed through it in about a week or two because he's such a gangster. And then we started collaborating on the Tiny Tape Out project. He added a Verilog export, basically, and an 8-cell standard cell library. And that's been really useful because even for people with programming experience, if they have no prior HDL experience, I find that drawing a schematic makes it more obvious that you're designing hardware. Mm-hmm. Whereas if you come to Verilog and you've been writing C, it's very easy to think that you're writing an executable program for a CPU, not designing hardware and joining wires together and instantiating devices. Whereas if you draw it out like a KiCad schematic, it's kind of more obvious that it's all going to be running in parallel and it's all made of separate components that are all joined together with a network of wires.
Mm. Great. So now at that time, so basically you had 150 in the first one. You kind of started moving more and more and more slots being filled. You said up to 512, but it seems like people are also doing more complex things as we kind of move along in the
we had well. So there was a really big set of limitations made by my initial design choices about just trying to get something out there quickly, which was join all the designs together with a scan chain. So that's easy to execute, but you get massive latency if you've got a few hundred designs in there. Because you have to clock your inputs all the way through to the design that you want to be active and then clock the outputs all the way through to the end. So we ended up with a kind of sampled I/O system that ran at about 10 kilohertz or so, pretty slow. And then I burnt 9 I/Os on the design selection parallel interface. So we had like a little dip switch on the board. You enable design 128. And
how many do you get? How many IOs total do you get on an MPW wafer?
On the eFabulous pad ring, which is kind of you fit your design inside that, there's 39 IOs.
Oh, okay. Yeah. So then
you're fairly limited. And you need some there's like a configuration firmware you need that needs like 4 pins of flash, and then there's reset clock and power and stuff. So after I burnt the 9 IOs on a parallel design selection, we only had basically 8 ins and 8 outs.
Yeah.
And Tiny Tape Out 2. So Tiny Tape Out 1 was like a free experimental one that we didn't guarantee. And then Tiny Tape Out 2 was the first one that people could pay for. So I think that was when we last spoke. And then 3 was the last one on the scan chain. At 4, we were like, okay, this is happening. Let's go back and correct my bad initial design decisions. They weren't necessarily bad, but it was just like getting the job done in the time allowed, Now we're going to do this a bit more seriously. So let's switch everything out for a fast multiplexer and throw away the parallel design select and change it for a serial one and use those extra 8 IOs for an additional 8 IOs.
That's good. And so that was actually, now it was, you had to go and design kind of the dinner plate that everybody's dinner sitting on, right? That's kind of the idea.
Yeah. And that's like a classic engineering choice of you want to make it as simple as you can possibly make it without it being too simple.
Right. Yeah. I guess I still don't have I've seen some of the stuff and you've linked some of the designs. What would be a typical Tiny Tape Out design that you've seen? Yeah, typical is a bad word, probably. What are some interesting ones, I suppose?
Yeah, there's a ton of interesting ones. Well, we also, with Tiny Tape Out 4, allowed you to join multiple tiles together. So then you can, the biggest design you can get is 2 times 8 tiles. And then that's about enough for 20,000 standard cells. And we have, on Tiny Tape Out 6, we saw a Linux-capable RISC-V.
Wow. Okay.
There's still limitations in that. Because there's no room for memory really on these old processors. So the memory is external, so that slows everything down.
Mm-hmm. But it also benefits from the new I/O that you freed up too.
Yeah, QSPI, flash, and SRAM.
Yep. Well, that's pretty cool. I mean, and Linux capable. I feel like that's like that's a flexible term too, right?
Yeah,
how much Linux?
It's meant to boot micro Linux.
Yeah, I got it. Cool. Yeah. But still, very impressive. But does that mean then that person that did the micro Linux capable processor design, they did all that in Walkme, or did they?
No, they used Verilog. Yeah,
Verilog. Okay.
Yeah. So what we kind of breaks down after maybe 20, 30 standard cells. I think maybe the biggest design I've seen in Walkme is maybe 50, but it starts getting really like a nightmare. And you're like, now I understand why people invented hardware description languages.
Yeah, right.
If I want a register of 16 flip-flops, that's really annoying to draw. And I can do it in one line of Verilog.
Because it's a for loop, is that right? What is a for loop?
No, you just say like my register 15 down to 0, and then it's bam.
Okay.
Yeah.
That's pretty cool.
And then if you want to build a full adder to add 2 registers together, that's just like reg 1 add reg 2, and you haven't had to like draw 40
NAND gates and
ands and carries, and I mean that is cool to do that once.
Sure. Yeah, right. Well, and you had mentioned at the beginning, kind of also being able to target high schoolers, right? So like Walkme can enable people of all Walkmes of life.
Yes.
Delirious. So are you actually seeing that come to fruition? Like, is this making its way into college curriculum, high school curriculum, stuff like that?
Yeah, we did a project with Oklahoma State last year, and they had a bunch of high school teachers in on a course, and then they all did a tape out with Walkway, and now they're using those in their high schools. That was a National Science Foundation funded project. So we're seeing more of this. We've got the 50 billion EU and US Chips Act, and a lot of that money is being spent on fabs and so forth. But
Intel.
the big companies have big nets to catch the dollars, and good lobbying probably.
That's right.
But all the Chips Act all say, but we're going to be missing 50,000 people to do the designs or run the fabs. So there's recognized that there needs to be an effort made on the educational front, and probably there's got to be worked on in tantalizing people away from well-paying JavaScript jobs. But also recruiting more people from high school into microelectronics and kind of revitalizing microelectronics courses. And one way of doing that is to expose younger people to microelectronics earlier. I mean, I don't know about you, but I had no concept of this kind of stuff when I was in secondary school. That's what high school is called in the UK.
Yeah, no, I mean, maybe I watched a video on chip processing at some point, but nothing I had nothing.
Yeah. So just showing kind of, how a chip is manufactured. By the way, if people haven't watched my IHP fab tour video, you should definitely check that out.
Yep, definitely. We'll link that in too.
Link that in. Yeah.
It's interesting. I'm not sure I would tell my children to go work in a fab. Would you?
No.
Tell my children?
I would tell your children.
Got it. Good. It's fair.
No, it's just that spending one day in a clean room was, it's something that is hard work. You have to get adapted to, like any job that involves wearing protective clothing.
Mm-hmm. Yeah, I mean, I used to do it. I did it for 2 years, and I don't think I would ever recommend it to, like I said, family members at least. I think certain personality types actually do thrive in that.
Yeah, and like you said, I interviewed the guy, some of the guys that I met in IHP, and they, on the whole, loved their jobs, and because they had very high attention to detail and loved refining processes and keeping everything very controlled and in step and measured and precise.
Yep.
It's definitely not my type of job.
Agree. Same. But like you said, I mean, you're really showcasing. I mean, that's the process side, right? That's the manufacturing of the chip itself, and there's people that gotta design the thing that's going on the wafer. So depends. Where
I think the argument that you make though is that we keep running into these barriers. So we're getting more and more transistors on a chip, but you kind of hit the top maximum speed you can hit, and you hit the top power that you can hit. You hit the top number of cores that you can hit. And now people are more and more looking at the alternatives of general purpose computing and doing more application specific. But designing chips is hard work and takes a lot of effort.
Yeah. So and usually you need an application that can bear the cost and the upfront costs and the ongoing maintenance costs. But
it totally depends on your predicted volume. Right. An interesting thing that I learned the other day was if you're doing volumes of tens or hundreds of millions, your non-recurring engineering costs, your NREs, go to zero. And you're left just with your recurring costs, which is the actual manufacture, the testing, the packaging, your yield issues. And they come to dominate the cost of your chip.
I see.
And I think that
you're not saying that they actually cancel them out, though. You're just saying that as a fraction of the overall.
Yeah, that they tend to zero as you get up in the millions of tens or hundreds of millions, which is why I think that the big companies don't really care that the proprietary tools are so expensive, or the cost of maintaining a big engineering team is expensive, because it all tends to zero on these massive volumes.
Yeah.
But I think
if you make one mistake too, right? I mean, so I feel what they're really buying when they buy a Cadence license or whatever. What is Cadence? Is that one of the big ones?
Yeah, Cadence, Synopsys, and Mentor Graphics.
Yeah, right. So one of those, I mean, if there's anything wrong, they could very quickly get damages into the millions of dollars too, right? I mean, it's just like wacky.
Yeah, especially these brand like the super mega awesome teeny tiny mini micro nanometro processors. They are like hundreds of millions in mass cost, so you definitely don't want to mess them up. Like
I mean, you look at NVIDIA is like the most valuable company in the world now, like, and it's because obviously the output is super important, but they also dominate. Like I was just listening to a report the other day that was just like, nobody can compete with them because, TSMC is basically made to serve applications like that are going to be high margin, high volume, high needs, bleeding edge, that sort of thing. So,
well, we are in the middle of an AI bubble.
It's a bubble? Oh, I didn't know that.
Yeah, didn't you? Yeah.
Oh. Yeah. Matt, I thought you were going to come onto this show and announce that you were launching a new tool that has AI in it that makes it easier to make chips. Is that not why you're here?
GPT for chips.
Yeah.
That has been done, actually. In fact, Tiny Tapeout enabled the world's first ChatGPT design chip.
Yeah. And are people still using it?
Yeah, I think it's pretty helpful for a bunch of things. I mean, I wouldn't trust it for something expensive, but definitely for playing around with things. But the point that I wanted to make was, I think there'll be new niches opening for more application-specific stuff at lower volumes, where you do care more about the NREs because you're selling chips for a lot more money, but you have much lower volume. So then at that end of the market, your NREs dominate. So the cost of the tools, the cost of the team, that's an important thing. So then I think that's where the open source tools can come in as well.
Yeah. I mean, if we were to do a Venn diagram, sorry, of I think about the things that actually drive people to want to do, like Tiny Tapeout being one thing, like just a MPW wafer from eFabless or, just shuttle service type stuff in general. The reason people want to do custom silicon, I think about like things like power, kind of ad hoc security, maybe even having additional security stuff that wouldn't, be on general compute, size, capabilities that maybe aren't bog standard from like a chip maker. Like for some reason you need 16 serial ports or something weird like that. That's what I think about. Maybe are there other ones in there in that diagram?
I think, in my opinion, anything that is purely digital, you would I don't see any realistic reason why you would do those chips, at least with the PDKs that I play with. Because I'm also the PDK that I have access to is 20 years old.
Sure.
So if I'm doing a digital project, then I would just use a microcontroller and FPGA.
Oh, okay. So then where do you see the kind of the overlapping?
I think that analog and mixed signal is the unique selling point of low volume custom ASICs, because you can do stuff that you can't do in any other process. So if you concentrate extremely high performance analog with some radio, say, or a RISC-V core on a single die, then you're potentially making something that is really unique, that is hitting a niche in the market that hasn't been exploited yet because it's too expensive to do with the traditional tools.
Got it. Okay.
The other thing is, bear in mind, also for everyone that's listening, that I am really focused on the open source side of things. I haven't even used the proprietary tools. I don't have access to them. I don't have access to the NDA PDKs. So my viewpoint is going to be biased towards what you can do with the open source tools and what you can do with these older, cheaper nodes.
Yeah, but I don't know. I just feel like the industry, you go to something like DAC, like Design Automation Conference, and it's not like, you basically need to be at a big company in order to be there for that sort of thing. There's a lot of money in the industry because there are big companies doing this sort of thing, but their expected input into the, the kind of the hopper of students and, potential people that could do that sort of work. It's just, it doesn't feel like they're, aside from, they do have university programs and they do have low cost tools for university programs. It doesn't seem like there's as much of a general kind of entrance for other people.
Yeah. I mean, another interesting data point maybe is that we have quite a few designs coming into Tiny Tape Out that are from professional chip designers who
Oh,
are finally able to tape out their own designs when they're allowed to.
got it.
Because when you're a chip designer working for a company, then you're just doing what your boss tells you
Yeah,
because you're part of a big team on a big project that's
right.
very expensive and can't be messed
You're
up.
saying you get to use the Mentor Graphics license on the weekends, perhaps.
Unlikely that would be allowed. I mean, some people that I talk to wouldn't even be allowed to do a tape out on Tiny Tape Out because of the agreements that they've signed with their companies that
Got
they
it.
work for.
I'm sure they are well compensated for locking down those skills, but yeah.
Yes,
It's
generally, yeah.
unfortunate.
Yeah.
Yeah.
But we had a great 12-bit SAR A to D
Hmm.
put on Tiny Tape Out 7 by a Texas
Okay.
Instruments analog chip designer.
Really? What kind of
Yeah.
speed was the SAR?
I'm not sure. I'd have to check the repo. It's
Yeah.
I think one of the better repos in that it's got like a bunch of. You can tell it like a good analog design because it has a specification, whereas my analog designs are just like it should work.
Yeah, you just like, you drop a P channel here and an N channel there and yada, yada, yada,
Yeah. When the input
Yeah.
goes high, the output should go low. Done.
Yeah. Boom. Boom.
If you don't specify things like slew or, output voltage, then how can you fail?
Yeah. Yeah. Right. Just don't tell me. Just, I don't want to know. I don't want to know. Well, so you mentioned analog a couple times. And so where did the analog start coming into the tiny tape outs and really just more generally in your use of the PDK?
Yeah, so we brought it in kind of secret in Tiny Tape Out 5. So to be able to do analog, you'd first have to be able to power gate designs because you can't let people basically with open lane, you like write some HTL and it's like a fairly automated flow and you get your standard cells and it's already past DRC and LVS and maybe you've simulated it if you're good. And the design
That's a pure digital design you're saying, yeah?
Yeah.
Like,
And
okay.
that's they're usually easy to manufacture and they work pretty close to how you expected them to work. But analog is really quite a different process. You're kind of drawing things out a lot more by hand. It's it's much easier to say forget to wire up the power or reverse the power or short out the power.
So just like
You
board
don't-
design.
Yeah. It's like imagine designing with KiCad with no DRC, ERC, or like board to schematic rat's nest.
Yeah.
Very, very manual process. Easy to mess up.
I don't mean to bring it back to this topic, but I did see a thing that was an AI tool that said we're 98% accurate on helping with your components and like making sure your design's correct. And I'm like, I would never ever accept a 98% accurate DRC engine. Can you imagine that? Just be like, you'll be fine. No problem.
It's only $200,000. Why not risk it?
Yeah, right. Exactly.
Yeah.
It's wacky.
I spoke to Carsten Wolf the other day, principal IC scientist at Nordic Semi, who's an open source silicon enthusiast. He submitted a SAR A to D on Tiny Tape Out 6, one of his own designs. And
you did a video, I think we shared on here as well.
Yeah, I asked him what he thought about AI for analog, because that's something people go on about, because layout for analog is very manual. Yeah. And he said, well, where would you get the training data from? Because no one publishes that stuff.
Yeah, that's a good point.
Yeah.
Yeah, I just feel like they're going to be like auto rudder style, just like shuffling stuff around and just be like, oh, this will probably work. We're going to just simulate it over and over and over again, sort of thing.
Yeah, I mean, there was I think an interesting application for Tiny Tape Out is if you did build one of these tools, you could do 100 variants of your analog layout and put them on each of 100 slots on Tiny Tape Out. By now
you're just trying to sell, Matt. I was we will give you a 2% discount. 2% discount for the 2%
if
error.
You come with code Chris Gamble says, I'll give you a 2% discount. Yeah.
Chris Gamble hates AI as a code, right?
One more data point from Carsten's interview was he's told me that Nordic only moved away from 130 nanometer process like a few years ago. So, they built their brand and all their IoT integrated radio stuff on 130. So you can do like a ton of great stuff on these older nodes.
Yeah. Do you know what family it cut off at? Was it like the 52, the 53?
No, I don't know. No, sorry.
I would have figured the 52. Yeah. Didn't make it the 52 for a while. But yeah, I mean, like the actual feature size of like, when you have like a Bluetooth chip or a Wi-Fi chip, you look at like a die shot of like a ESP32, they've got massive structures on there. You need a processor still. There is a processor, but like,
yeah, the analog
get big caps and inductors.
Yeah.
Right.
And 130 nanometers is quite a sweet spot for analog designers. It's got good performance. So yeah, we had to make this power gate so that designs could be turned off if they're not enabled. And I got help from Harold Pretel, who's a professor at JKU in Austria. He's helped a lot on advising on the analog side of things. And he submitted a super simple design, the only analog design we put on. Oh no, we did put 2 analog designs on Tiny Tape out 5, a ring oscillator and a DAC and a transmission gate, power gated. And we just got those chips back and they work. So that was a relief because 6 and 7 are both based on that.
Yeah, we made some assumptions and we may have made a bunch of garbage sand.
Yeah. The pipeline is long.
What is when you do I still get anxious when I'm like releasing a PCB just to like, JLC or something like that. How nervous do you get when you're like ready to cut a release?
I used to be very nervous, but now we have one of the awesome things that Uri's brought to the team is all the continuous integration stuff. So we started with that fairly early, but now it's basically everything is in GitHub. This is another nice thing about the open source tools is you can install them on a GitHub virtual machine and everything is public. So when you submit
you get free compute then too, right?
Yeah, exactly.
Yeah, that's great.
It basically opens a pull request. So on your repository, it builds the GDS and checks it and runs any simulations verification. And then once the green lights are all lit, you can basically open a pull request on the chips repo, and then it gets integrated. And then we then run our own verification, simulation, formal verification, equivalence checking, like all the CI stuff. Generate the final GDS files, submit them to eFabulous, run the pre-check there. And we're kind of running this continuous integration like all the time that the shuttle is open. And then when we close our shuttles like 1 week before the eFabulous deadline. And then it's no longer stressful.
That's good. Okay. Oh, that's great. And in terms of like when someone does a pull request to the shared wafer, then is it like so if I uploaded a design that's like a ring oscillator, is it just like I get assigned a number and then there's like a folder that it corresponds to my design? Or like who does that integration piece?
Well, we integrate it all into the die that is Tiny Tape out, and then we submit to eFabulous, and then they integrate those 40 projects into the one reticle.
Oh, so they actually do the glue? Who does the gluing? I guess when I think about like Osh Park of yesteryear, right? It'd be like laying, like, basically dropping these designs and like fitting them, right? And now there's standards. There's like, you have a standard size, you said 512, like standard blocks that you have.
Yeah. So maybe consider, it's good. It's a good question. I guess, I kind of feel like Tiny Tape Out is the Osh Park of ASICs, but in this particular case, eFabulous is the company that is doing that final gluing all the designs together and submitting them to the fab. We don't talk to Skywater.
Oh, sure, but that's more like Osh Park used Royal, right? Like at one point, and so like eFabulous would be taking on the role of the board house, right?
Well, they still don't have the fab though. Yeah. So it's more like eFabulous is Osh Park, and we're a customer that takes a small PCB
and stuff together.
Divides that small PCB up into another 500 tiny PCBs.
Subdivisions on subdivisions on subdivisions.
Yeah,
what is
the PCBs are so expensive in this case. Even though eFabulous are bringing the price down to $10,000 for 10 square millimeters and 100 chips, which is actually great value when you compare it against the things you can get from Europractice and so on. 10 grand is still too much for the average hobbyist.
Is that price dropping? Like, I don't actually know the economics of like, maybe eFabless is like making it more efficient and they get to, kind of basically grow their margin over time. But I would imagine that a mature process can have more efficiencies and that they could drop their costs eventually, or they'd be forced to by just supply and demand sort of thing.
Yeah,
so
maybe.
Like, is that $10,000 ever getting cheaper, or not that like with Tiny Tape out too? It's not expensive. Like, this is amazing that it's so available. But I'm just curious about general costs. I mean, maybe it's a Mohammed question instead of a Matt question.
Yeah,
I'll let you answer.
Maybe. I mean, I know that
Mohammed, can you tell me all of Mohammed Qasim as well, who has been on the show? Be like, can you tell me all of your business secrets, please?
Well, that's more of a fab question, isn't it? Because you get your massive loan for billions of dollars, and then you build your fab and buy all your machinery, and then you're basically selling wafers until you've paid off all the machines. And then
it's an annuity, reverse annuity. Yeah,
every wafer you make is money in the bank. So it's kind of, you're going to try to get as much as you can. So I imagine that as more processes are considered trailing edge, the price will continue to lower.
Yeah, that's what I figured. And like I said, maybe eFabless has it put into their model where they have a flat price that over time they basically get more margin. That would make sense. They're basically taking a risk up front sort of thing. But I am generally curious about, like, I don't know what fab costs do. Like, there's a lot of actual material costs and just operational costs for a fab, like just weird gases, and like you got to have crazy ass, like a Klystron machine, like those things that like the implant machines. You ever see those? Did you see those on your tour?
Yeah, they're like mini particle accelerators.
Exactly. Yeah, except with like boron gas and like phosphorus gas, and it's just like it's basically like it's like a particle accelerator with like poison, like in there, It's wacky, Yeah. It is magical bits of sand, of course.
Yeah, so, and huge feats of engineering to build these individual machines as well.
I know. And I take them for granted so often. I'm just like, oh, why doesn't this chip work? Why is it so expensive?
Yeah. Yeah. And it's crazy that they even work at all.
Yeah. This RISC-V chip is 12 cents instead of 10 cents. I'm upset.
Yeah.
The customer's always right, Matt.
You've got to find a customer that's willing to pay high margin chip costs.
I have to find them, or you? I think you have to find them.
Well, I've already found them.
Are you talking to them right now?
Yeah. Well, I mean, Tiny Tape Out is an example of a high margin chip, or like a high value chip. The chips are $100.
Yeah. Right. Exactly. Yeah. So $100, you get how many chips? One chip? Two, three? How many do you get?
One chip. Yeah.
One chip for $100.
Yeah. By the way, we increased our prices. So for Tiny Tape Out 1, 2, and 3, that was all $100. Now it's $300.
Mm-hmm. Wow. And people are still A-okay with it?
Yeah. Didn't get any pushback at all.
That's great. I mean, at a certain point, you're really offering the experience of building a thing, holding that thing in your hands. Like, that is, excuse me, super magical, right? I mean, like, to the point where I feel
also did my classic thing of just like chronically underpricing the product and not taking into account like all the work that goes into making something. But $100 was, I mean, when I originally came up with the idea in my head, it was like $100 tape out, but I have like enough business sense to know not to embed the price into the name of the company. So I changed to Tiny Tape Out, but kept the $100 price mark, but too low.
Yeah.
But due to the eFabless sponsorship, the first 100 customers get it for $150. So we only actually, for individuals, the price only went up by $50. But for universities or like companies that need an invoice, or after the first 100 chips are sold, then it goes up to $300.
Yeah. Buy now. Okay, so let's talk a little bit about. So obviously you have a course too. We've talked about that when you've been on the show in the past. It's well regarded by all.
Before I forget, let me just say Tiny Tape Out is open now and closes September the 6th. So if anyone's listening and they want to do a ASIC tape out, go to tinytapeout.com and have a look at what's going on there.
So that's like 6 weeks away. So like that's a good lead in here too. Can I learn chip design in 6 weeks?
You could like draw a few standard cells in Walkway, run it through the automated flow, and then get a custom ASIC made and ordered in a few hours.
Okay, let's move up from there. What's the next step up?
The next step would be like learning how, like kind of going back to what we were talking about with Walkway, like what's a full adder? How does a register work? How about like a linear feedback shift register or like pseudo random number generator?
Okay.
Draw like a bunch of these kind of fundamental digital building blocks in Walkway, test them all, take them out. Next step up, learn a hardware description language like Verilog or one of the newer ones like Spade or...
He's going to say Rust. Everybody says Rust.
Yeah, I think probably Rust is coming soon to chip design. I don't know.
Yeah. If
there's a bunch
here's the thing. If Rust is coming anywhere, you're going to hear about it from the Rust station. Yeah. So don't worry. You'll hear. Yeah, I see all you Rusties.
Rustans.
Yeah.
Rustations.
Yep. They do great work. I just,
Yeah. As long as you eventually end up generating Verilog, that will work. That plays nicely with all the open source tools. So there's one that is not a high-level synthesis. It's more of a hardware description language called Amaranth. There's a new one, newish, by Whitequark. It's under a lot of development at the moment. Lots of community-driven RFCs and so forth. Good one, worth checking out. And that compiles down, that's the wrong thing to say, but you end up with Verilog, and then you can put that into your repo.
Yeah. Whitequark is kind of like Uri in terms of like the echelon of just producers, just like wacky amounts of output.
Yeah.
They're very impressive.
Catherine Whitequark. Yeah. And did you see she recently showed full in the browser HDL to FPGA bitstream and program the board? Like I think she did it all on a mobile phone.
Oh my gosh. Yeah. Yeah, that's what we're talking about here. Like that level of that's very impressive. Yeah.
We've got a GitHub action now that also generates the bit streams for ICE40 FPGAs, and we have this
cool
little replacement board that fits on top of the dev kit instead of the ASIC. So for development, you can develop on an FPGA, and then when the ASIC comes back, you swap them over.
Oh, that's a great idea. Okay, so basically, because you're starting from Verilog, that can compile to just FPGA land
bitstream.
What about the size? I guess probably the ICE40 is probably much bigger, right? Like it has a lot more headroom in there.
The up 5K is the same one on the 1-bit squared Icebreaker, which by the way is my recommended FPGA of open source choice if people are after an FPGA.
Okay.
Shout out to Esden. And I think it's 5,000 logic elements. So that would be maybe like 2 or 3 tiles worth of tiny tape out. But it does come with block RAMs and DSPs, which are...
Got it. Okay. Yeah. So like the Linux capable one that you described earlier in the show, that would not fit on there, but maybe other ICE40s that are larger.
Yeah.
Got it.
Yeah. I mean, it's a good for people that are like beginners. It definitely covers you.
Yeah. Okay.
Yeah.
That's great. What about, so walk us through again so I had said 6 weeks. What is the most you think someone could do in 6 weeks? Not saying they should do it, but like, maybe what have you seen that has been the most someone's done in 6 weeks?
I saw someone do a GPU.
Really?
Yeah, and that took a lot of work because they had to read a lot of papers about the kind of fundamental architecture of GPUs and how to... And I think not everyone, but a lot of people know they're like a massive array of multiply accumulates, but how are they actually fitted together, and how would you then be able to load something onto that and make it work? Like the devil is in the details. So they spent, name's Adam. They did like a tweet thread on Twitter about it. Yeah. And we've seen FPGAs as well. Again, I wouldn't recommend that for beginners.
Okay.
There's a really cool RISC-V course by Bruno Levi, who walks you all the way through nothing to building your own RISC-V processor.
Oh, cool.
And that would fit on like 1 or 2 tiles worth of tiny tape out.
Right, because RISC-V stuff can be basically as big as you want. Like you could put lots of memory, you could make like super crazy large processors, right? But
yeah, and
most
you can
of the
do
time
things
when you're
like
learning,
you could have like out of order or like multi-stage pipeline, so it gets bigger, or you do like bit serial stuff, so it gets smaller. Like personally, what the kind of things that I like to do are the kinds of things that surround the CPU core. There's already so many RISC-V CPU cores, so but they're not really much good on their own. They need GPIO drivers or like the RP2040s PIOs or
yeah,
PWMs or A to Ds or D to As or timers or interrupts or like all of this. When you like buy an Atmel chip and it's got like 40 really cool rock solid peripherals,
yeah,
all of those things have to be made, and they're an interesting thing to try making. And it, I think, also as most people that use tiny tape out aren't going to become chip designers. It will just fill in an area of their knowledge they didn't have before. So if you make a serial UART for a RISC-V processor or something like that, so that when it runs on an ASIC, it's just printing out like a pre-programmed, "Hi, Chris, welcome to your first ASIC," and that's all it does, and then counts up to 100. Or you have a little bit in there that is like I don't know, Prince of Fibonacci sequence or something.
yeah,
But then next time you're writing code for a serial port, you're more thinking about, okay, yeah, the data gets loaded into this thing, and the serial port's going to go off and use a clock divider to clock this stuff out at the right board, and then raise an interrupt, and then that's when the CPU will get interrupted and load the next byte of data in, and you kind of get a bit of a better understanding of what's going on under the hood with all these
right.
libraries and levels of indirection that we all take for granted these days.
Yeah, and that is good. I mean, like I think let's just say earlier Chris would have been more like grumpy about that. Like, why do I need to learn it? But I think as I've done more programming, I do think there's value to understanding it, right? So it's not a true black box where it's just like, well, I wrote it in there. Why didn't it do what I wanted it to? Like it's actually understanding some of the underlying does have benefits outside of.
Yeah, I think I'm a big believer in like a broad level of knowledge that gives you jumping off points, or at least that there is a field that is focused on this, and then you could be like, who do I know that is an expert on DMA? And then you find that person, and then they like accelerate your program by 1,000 times by like correctly writing a DMA driver.
Mm.
Whereas if you have no idea about how that stuff is working under the hood, you're like, well, my processor just is too slow for my application, so I need to buy one that's 1,000 times faster.
I gotta pay more. Right, exactly. Yeah.
Yeah. No, like you need to enable this bit in the DMA register, and then you're going to take advantage of this like incredibly accelerated pipeline to take memory and pump it out of the D2A.
Mm.
I'm a fan of VGA projects, stuff that puts stuff on these panels. We have a community developed little VGA P mod by Leo Moser, and we're going to run a competition for Tiny Tape Out 8. It's kind of in the works, but it's like ASIC demo scene. So
like one cell
has to fit in one tile, uses the standard P mod and PWM audio, and then we'll like give prizes to the coolest, most impressive designs, and have like categories like best sound, best graphics, best racing the beam, best newcomer.
That's great. I like that. I like that a lot. Yeah.
I think we like one thing that we've heard a lot about why people like Tiny Tape Out is kind of working within the limitations. How much can you really do in 1,000 standard cells?
What would you, if you had to guess, like maximum? I guess you've seen a lot of these now too, right? You kind of get to sample all these. In terms of like single tile, what's the most? I guess you said you've seen a very tiny RISC-V or not?
Yeah, I've seen RISC-V or like just very many CPUs. They're a very common thing.
Oh, really? Okay.
Yeah, and I think
because you get to start from other people's IP, or you think people are just kind of like re-implementing in Verilog?
Yeah,
or
I think
why?
Is like after you've built a full adder and a state machine, you're halfway there to a very simple CPU.
Sure. Yeah.
So it's like a common. I mean, it's still on my bucket list, to be honest.
Really? Okay.
Make my own CPU, just to, especially after playing with that cool Supercom exploded view 4-bit CPU badge.
Oh, the Voya. Yeah, I think I have that one.
Voya's awesome badge. Yeah. It's like you really kind of see. Okay, you need like a clock, you need an ALU, you need some registers, you need like you need a data path. You could see it coming together in a few hundred lines of Verilog.
Yeah.
But yeah, I would start off with simpler stuff. And after you've got the CPU, then you need like an assembler and a compiler and all the gubbins if you want to make it nice to develop for.
Mm-hmm. You had said in your list of tools that you're seeing, so you're seeing new tools come up as well, like new tools for people that are building stuff. Is that like compilers, or is that other tools that are
yeah, like new hardware description languages. There's one called Surfer that is a browser-based waveform viewer. There's the one that everybody uses is called GTK Wave. Again, in the open source world, the one that everyone uses. That's quite interesting for us because we would like to plug that into our GitHub action flow so that after it runs the tests, you can then load the waveform in the browser. Yeah, then Yosis HQ's got a formal equivalence testing tool, so you can take your incoming hardware description language and then formally prove that the output of the GDS compiler essentially is correct.
Can you remind me? So I remember when Claire was on the show, talked about formal verification. I'm not sure I understood it then. So like, how do you prove that it's correct?
You use a SAT solver, satisfiability solver, which is I think a nice. There's a cool blog post about this on the Yosis HQ blog. If you've not checked that out, then it's worth a read. And there's one by a guest post on using SAT solvers to solve Sudokus. And I think that's quite a nice way of thinking about it. Everyone's like knows what a Sudoku is. So you basically say, all these rows have to add up to this, all these columns have to add up to that. Is there a solution that satisfies all these constraints? And then a SAT solver is a type of software that can basically say yes or no. And if it says yes, then it's not just a yes, it's that there's a mathematical formal proof that can be made to show that that is true.
Got it. And it's not just doing brute force.
No.
Like just try all the things, because that would take forever, right?
Yeah, it works a different way. I mean, it has its own strengths and weaknesses like every other verification technique, but
yeah,
you can do a lot in a simple thing. Like we have formal verification on the tiny tape out multiplexer, and there's like just one or two assertions that basically say, so we instantiate the chip, we connect all the outputs to all the inputs, and then in a design we say, assert that my inputs equal my outputs, and allow the solver to set the outputs to be anything that they want.
Mm.
And then the solver can pick any designs in any of the multiplexer and set any of the outputs. But if the multiplexer is working, then the inputs are always going to be what the outputs are if we've made a loopback on the outside of the chip. Whereas if one wire was missing in one mux location, then that formal assertion would fail. But I didn't have to write a program that checked it in every position, because the SAT solver would find if there was a place where it would fail there.
Yeah, I think that just highlights to me like the amount of helper software that's in, like you mentioned, that's in the CI loop and now just enabling all this stuff. Are you seeing new tools? I mean, so OpenLane, OpenRoad, I think, did we have someone on that was doing that stuff? No, I think he was on a different podcast.
Andreas Ulfsson of Zero Ace, not to be confused.
He was on the show.
His company have a tool called Silicon Compiler, which is another Verilog to GDS flow.
Got it. Okay. Yeah, and he had been doing some of that stuff, I think, for the government too, right? The U.S. government, some of the OpenLane, OpenRoad stuff. There's been a lot of shows, man.
Yeah, he was a key figure in actually getting the open source tools developed. So he was working for DARPA and funded the development of OpenRoad. And OpenRoad is like the core set of tools that are now used by pretty much all the open source ASIC flows.
Got it. So are there new tools that are coming down that pipeline in terms of like open source capabilities? And like, maybe you don't have visibility into that? I really don't. I don't watch that scene. I mean, you just came back
There's
from a
there's a
conference, right? So,
new version of OpenLane called OpenLane 2, which is
oh,
like an upgrade of OpenLane.
okay.
And the fundamental tools like replace and Triton router and these kind of place and route tools and legalizing tools, and there's one called OpenSTA for static timing analysis. They're all like in active development.
What do you? Sorry, legalizing tools. What does that mean?
Yeah, getting a bit into the details there. So,
well, yeah, sure.
Place and route. The first part is placement, and there's actually some really cool animations I've seen because it's the placer uses an electrostatic model, so it like puts a negative charge on all the standard cells in software model world, and then they like repel each other, puts them all on top of each other. They all blow out into a cloud, and then they're like pulled. The other side of the cost function is pulling together which standard cells should be together. So it kind of like jiggles them around and wiggles them, and they kind of
like trying to
together.
Optimize for shortest route, that sort of thing, or like shortest distance.
It's one of these impossible problems to solve that is kind of well handled by these kind of models of nature. And then for the routing, a common model is called simulated annealing, which is like annealing metal, kind of crystallizing and melting and recrystallizing.
So doing like biomimicry applied to chip design.
Exactly. Yeah. It works surprisingly well. Anyway, after
the old ways are the best ways, Matt.
After the global place is done, all the cells are in a cloud, but they need to clip into the power distribution network, which is very regular. So the legalizer basically pushes all the cells so that they clip into the right place and maybe flips them so they get the right power supply.
Wow, that's wild. And I mean, like, and then the level that I, as a complete noob, would interact with that is none, right? I would just be like, it's just running. So
yeah, essentially all of that is abstracted in the GitHub action and then inside OpenLane. But if you want to, you could download the tools, run them on your computer, and then you can like pause at any part of the process and inspect where the design is at that moment. So
cool.
You have like full transparency into what's going on if you want it.
So then when you do, so you've been doing some analog stuff, you've been doing some analog like experimentation and learning and things like that. All that same tooling applies. I still don't quite understand the analog versus like kind of the more the Verilog flow.
Yeah, the analog is different. To start with, you make a real rock solid specification, because after you do your schematic capture and start your layout, if you have to change your layout or your schematic, you basically have to
start over,
reset a lot of your work.
Yeah.
So you really work hard on specification to get to know what success is, and then you don't want to change it. That's not what I do.
Well, you're learning. I mean, that's okay.
I'm learning. Yeah. So
you're learning in the old head on desk mode, right? And, like that's the
yes. Well, I'm just like, what would be a cool design to make a voltage reference? I'll download a bunch of IEEE papers and read them and find a circuit that looks like I could do it, with the minimum number of transistors. The biggest circuit I've made so far, I think, was 7 transistors, and that was too much, to be honest. So,
wait, and does that mean that you can then put a Zener in silicon? Like you can design that in and as a thing?
I'm not sure about a Zener. You can definitely make a diode.
Okay, diode. Yeah, I guess so you have access to more of the building blocks, so you can basically pull out diodes and things like it, or are those also?
Yeah, the main thing that you're doing is drawing MOSFETs, resistors, and capacitors.
Okay.
And one thing that is super interesting that I've found out recently is if you draw a capacitor or a MOSFET and they're close to each other on a die, on a layout, they can be very well matched, but they won't match on the next wafer that is produced. They might be 10% off in value.
Why is that?
Because things change in the process. You've got this insanely complicated stack up, and just a few microns thicker solder mask on the next wafer is going to give you slightly different performing MOSFETs. So
Wait, how does that work? So you have to have like lots of like checking and.
No, you do it by designing with ratios. So like you do the ratios between components, not precise values of components.
Huh.
So imagine like a really simple voltage divider made out of resistors. Those resistors might be different from wafer to wafer, but if they're matched well to each other,
I see.
if you get three that are exactly the same size and you put in 5 volts or say 3 volts at the top, you get 2 volts and 1 volt out.
Yeah.
It doesn't matter if those resistors have a different absolute value on the next wafer.
Right.
You're still going to get 2 volts and 1 volt.
Got it. Okay. That's interesting.
Yeah.
What does this tooling look like? Because like, okay, so I had a very bad experience with, took an analog chip design class in college. I got a D. I barely passed. I probably shouldn't have passed, to be honest. I think my teacher took pity on me, but it was pencil and paper. It was terrible. It was colored pencils.
Yeah. I mean, that's like, if you want to learn it properly, that's the way to do it. And there's kind of,
I don't want to hear that. I want to hear that. No. The teacher was wrong, and he should have given me more tools, Matt. I wasn't in the wrong. He was.
Well, you should
despite
start
all
with
the people
Silhouette.
that went on to design actual chips for my class.
Yeah. Yeah. So just you should start with Silhouette to get just a rough idea of what's going on. And I know Uri and Torsten will be sad if I don't say Silhouette.
Silhouette. You gotta do it, man. I think that was right as. When did we mention Silhouette? I remember mentioning Silhouette on the show at some point. It
wasn't public last time we spoke, and now it's public, and so are all the lesson plans. And they're available in Spanish as well.
Okay, great.
But that is like you draw the layout and you simulate the MOSFETs and the capacitors and the resistors. You build simple circuits. The thing that's missing from that is schematic capture. So the reality is you do the schematic capture in a tool called Xscheme, and then you simulate that. Once you're sure it satisfies your specification, you do the physical layout of drawing the transistors and the resistors and capacitors and wiring them all together.
Okay.
And then you extract the circuit, which includes parasitic resistances and capacitances, and you check that when you simulate that, it still fits your specification.
Huh.
And then if you're cool, then you tape that out. I did a video about this recently on the 0 to ASIC course YouTube channel that like showed how I did it for a simple DAC, I think, that I did recently. So if you want to see the tools in action on YouTube, check out the channel.
Okay.
And let me just also mention I've got a new course under development, the analog version of the 0 to ASIC course. And
nice.
If people are interested to get on the wait list for that, then it's bit.ly/analog-waitlist.
We'll put a link, of course.
Put a link in there.
Yeah. What would people expect to have at the end of that?
Things like op amps are quite common because you only need 5 transistors for an op amp. DACs, like resistive DAC. Like one of my first projects before I even started with transistors was doing things like build a little digital block that does a sawtooth waveform and then plug that into an R2R DAC and just like make a sawtooth output. I did a twin T oscillator. I got inspired by Alan Volk's YouTube channel.
Okay.
Because you can do that with a notch filter in an op amp. So I stole someone else's op amp.
Oh, nice.
Built a notch filter, and then that just like the notch filter goes in the feedback path of the op amp, and you get a relatively sinusoidal output, hopefully at 2 megahertz in my case.
What are the relative, you mentioned you can put resistors and capacitors in there. What are the relative values you can do?
Yeah, good question. If you devoted like your entire area of a tiny tape out tile, you would reach maybe 1 picofarad.
Okay. Yeah. And it would be 10% different the next time you make it, right?
Yeah. Capacitors match very well on the same die.
Yeah.
So they're like, you want to use them and transistors more than resistors.
If you're going to use one, you should use 2, huh?
Yeah, and connect and use symmetry. You got all this stuff with symmetry and layout and dummy devices. It's really gets complicated. Boris Merman is a lecturer, and I've been chatting to him as well about. He's got like many years of industry experience and now lots of experience in lecturing. And he's written a couple of books, and they're published on GitHub. If you look up Boris Merman on GitHub, you'll find them. And he made copied this from his book. How does microelectronic design compare to board level? I think that's quite interesting. So board level stuff, you're trying to do like hundreds of components, whereas hundreds or thousands of components is totally fine for ASIC. Resistors are in the range of 1 to 10 megohm on a board, and capacitors 1 picofarad to 10,000 microfarad, whereas on ASIC, you're like femtofarads to picofarads range. Resistors and capacitors on board level you can buy like matched like to 1% if you buy the expensive ones. But on an ASIC, although they can be matched to 1% on a die, they'll only be like 30% across wafers. So that's where where you're wanting to design with ratios, not absolute numbers. So that's where a lot of the clever stuff happens in analog design. It's like way beyond me at this moment.
I feel like I'm having the same feeling that I had the last time we were on the show, where I start to look at this stuff and I'm just like, how does anything work? Like I know like at the bottom there's physics and you kind of work your way up, and there's all the process stuff and all the tooling that makes it all possible. But like, hot damn, like there's just, it's amazing.
Yeah, I mean, each one of these topics is like years of research and PhDs.
It's a graduate degree if you want it.
Yeah, at the Free Silicon Conference, I was chatting with guys who spent like 15 years only designing PLLs.
Wow. Right. And I can imagine those folks as well that are like PLL's masters. They know chip design generally. I can imagine them being like, yeah, I want to make a processor. I want to make a whatever, like I feel like because of the complexity of and like the importance of something like a PLL and a chipset, you probably do get kind of pigeonholed. It's kind of that's a negative connotation there, but like you get specialized because you need to be specialized because you need to make it better than everybody else, right? Like,
yeah, I think that happens in like every industry. Basically, things get so specialized that you have to, if you want to be useful, you have to. In a big company, let's say, in a startup, totally different story. Yeah. And I think, we will see more silicon startups, especially now with like more niches available and kind of the end of the gains of Moore's law and general purpose computing.
Do you think, I mean, we mentioned the CHIPS Act. Do you think any of that will trickle down to this crowd or no?
Yeah. I mean, it's trickling down to me and the open source crew already. Yeah, definitely. We're getting like,
okay.
I think I've co-signed 10 letters of support for NSF-funded educational projects in the US.
Oh, great. Okay, so like, that's great.
US CHIPS Act funded stuff. And then we've got, I don't know, like 5 or 10 universities in Europe that are developing their microelectronics courses. And typically you wouldn't get to do a tape out until PhD level. And we're basically saying, if you're doing electronic engineering or microelectronics or VLSI or computer architecture, you should do a tape out at bachelor.
Yeah. And then sooner eventually.
Yeah.
That's great. Cool. Well, that's really great, Matt. I mean, every time I watch your stuff, I'm amazed at how many things you're doing. It looks exhausting.
Delegation is the key.
Yeah, but still, I mean, like, it's great. It's great you're doing this stuff. I think we all benefit from it, and you're building a great team too. So yeah, we all benefit.
Yeah. I think that's a very underrated skill, is like the communication and the team working. And I think a lot of people, myself included, kind of get drawn into maths and science and engineering because we, maybe communicating and working in teams isn't the easiest thing. But I really kind of felt my powers were unlocked when I learned how to
with our powers combined
work better in teams and learn how to communicate. Because no matter how cool your project is, if you can't get it out there to other people, if you can't communicate it, if you can't work in a team, then it's like can die on the vine essentially. So, and the course and Tiny Tape Out have proved like incredible places to recruit from. So, someone does a tape out on every shuttle. They're ideal people to ask to are you interested in getting paid to do documentation or get paid to develop the next PCB? Or
That's great. Where can people find all your stuff?
tinytapeout.com, 0to-asiccourse.com, and yosishq.com.
And shoot, I forgot the name of it. Fuzzy Wigs? No, what is the
Silly Wiz.
Silly Wiz? That's it.
Silly Wiz is linked from Tiny Tapeout.
Got it. Okay.
The YouTube channel.
So go there for Silly Wiz.
Zero to Ace Course YouTube channel. Sign up for the mailing list. Like, subscribe, ring the bell.
Classic. There's the communication stuff he's talking about, folks. He's got to get people to ring the bell so that we can be dinged when there's new videos, and I'm enjoying them. So.
Yeah, actually, let me just share one last little anecdote. The 3D viewer, when I show that to people in the biz, they're like, this is pointless, because they're so used to seeing everything from the top.
Yeah.
And they know how everything is interconnected in their mind's eye. They understand. But when you're a beginner, being able to see it from the side or rotate it is so invaluable to understanding how these layers work together. But it's not included in any of the normal tools. So it's like everyone was like so amazed when they saw it. And that came from a community contribution. That came from Maximo, who also does all the amazing 3D Blender renders of the chip design stuff we do.
Awesome.
And
I can tell you another anecdote about that sort of thing. One of my college friends who started at Samsung when I did, he and another person took Google SketchUp at the time. Google SketchUp, now SketchUp, right? And they basically did the exact same thing where they as we were learning chip design, it was so incredibly critical. And like you said, the same thing. Like the teachers were like, "Why do you need this?" And we're like, "Because it makes sense now." Visualizing a capacitor cup on a piece of DRAM is like so tough to visualize. And yet when you start to see it and you zoom in, and that's great.
Yeah, it took me literally days of thinking and drawing to associate masks with 3D structures and MOSFETs. And that's a big reason why we did Silly Wiz and having the 3D graphics. And then the other part of that story is it turned into an incredible marketing tool because it made the kinds of pictures that people love to share. So it had this really unexpected community growing influence that was unplanned and unexpected. But I think it's an interesting story because I know a lot of engineers struggle with the marketing stuff. And one thing to maybe think about is like, what kind of stuff do people want to share, and how can you make that easy for people to share? And that will help you grow a community, and that will help your product take off.
Yeah, no, that's a good tip. It is sharing. Yeah, the sharing piece is important because you can't just blast different channels,
No, and you need like a sustainable growth if you're going to last without burning out.
Yep. Yeah, totally. Well, Matt, thanks for not burning out. Thanks for being back here and continuing Tiny Tape Out. September, what's the close date? September 8th?
September 6th is the next one. And then we've got the next one, I think it's in November sometime, shortly after the Hackaday SuperCon. If people are at Hackaday SuperCon in South Pasadena, definitely say hello.
Yeah.
I'll be there.
I hope to be there too.
Are you going to go? Oh, that'd be awesome. Yeah.
Yeah, we'll see. Last time I went, I lost my voice, and I don't think I think we talked about how I lost my voice. So
yeah.
Got to save the moneymaker. All right, man. Thanks for being here, Matt.
Thanks so much, Chris. Take care.